Good morning, ladies and gentlemen. This is Professor Junyin from National Yangming Jiaotong University, Taiwan. Today, it is my pleasure to share my research results about the embedded AI technology. The topic I would like to share today is embedded AI deep learning technology for ADAS applications. This is the outline of my presentation. First, I will give a simple introduction to the IVS lab, Intelligent Vision System lab that I organized. Then I will talk about the design trends and solutions for the embedded AI technology. Next will be the key component of the presentation today. It is about the AI decompression toolchain that we propose to solve the design issues of embedded AI technology. Then I will talk about the ADAS and ADS applications that we will apply on the embedded AI technology and to show the result. Then finally, I will give a simple conclusion. First, the introduction of IVS lab. The vision of our IVS lab is bright and light. That means to develop the brightest AI models teamed with the embedded AI chips. So our goal is to enable the embedded AI technology for AIoT, ADAS, and self-driving applications. Our target sensors include the camera and also LiDAR and the millimeter wave radar together. We use the AI technology to do the sensor fusion of these sensors to provide a robust and reliable perception about the environment on the ADAS and ADS applications. Here shows the ADAS technology we have developed before. That includes the lane departure warning, forward collision warning, pedestrian detection, traffic light detection, as well as the multiple object detections. And we also have the blind spot detection based on optical flow and also the deep learning technology. In addition, we also have developed some technology like ADView, HDR night vision technology based on different kinds of cameras, and also fisheye correction, and wide view video stitching. That means we support the 360-degree around view, and also the inclement weather processing. Here shows the hype cycle for artificial intelligence in 2021 proposed by Gartner. In the hype cycle, there are some technology that is related to the topic I presented today, which includes the Edge AI, Deep Learning Neural Networks ASIC, data labeling and annotation service, as well as the intelligent applications. This technology will be put into production in 2 to 5 years. Also, there's another technology called model compression that is also related to the presentation today. And this model compression will be put into production in 5 to 10 years. Finally, the fully autonomous vehicle that has a lot of design challenge nowadays and which would be put into production in more than 10 years. So we would like to propose some AI solutions that can deal with the design challenge of the embedded AI technology. The first one is to enable the AI vending machine service. The pain point here is how can I design an AI model? Because data labeling is a label work. And how can I reduce the large model size? Why there is mismatch result of the model running and AI chip versus the simulation? I think these pain points are the common difficulty that most of the AI researchers face. So the thoughts could be to use the automatic labeling tool, or to develop an easy tool to design AI model, or to develop an automatic model quantization and training tool. So the solution we propose here is called AI vending machine. That means we propose the AI decompression toolchain called EasyAIT to help you to design the embedded AI technology. The EasyAIT include EasyLabel, which is the automatic data labeling tool, and EasyModel, which is an automatic model pruning and training tool, and EasyQuant, which is an automatic model quantization and training tool, and also EasyHybrid Model, which is an automatic hybrid fixed point model training, and also we have hybrid CNN deep learning accelerators to achieve about 4 TOPS per watt at under TSMC 28 nanometer CMOS technology. That is helpful to realize the AI model that developed by the EasyHybrid model. Now I move on to the key technology that we propose for the embedded AI technology, which is we call the AI decompression toolchain. Here shows an example of video object detection used in the deep learning model development. First, if you would like to train a model for some specific application, the first thing you need to do is do the data labeling. The data labeling is lousy work and it takes a lot of time. So you will do some data augmentation about the label data to enrich the diversity of the label data. With enough data, you can do the model training. And after the model training, you can do the model quantization and porting on an AI SoC. So here I summarize some embedded AI sensing core technology. The first is data labeling. The second one is how do you develop the AI model? And the third one is how do you realize the AI model on a computing platform? So we propose an AI deep compression toolchain, including the easy label with the easy argument option, and also the easy model, and also the easy quant and easy hybrid model to help you to develop the embedded AI sensing technology. So here summarize the result of our proposed AI deep compression toolchain. The first is data labeling. We develop an easy label that supports the fast data labeling as well as the automatic data labeling. And in the automatic mode, it can speed up as high as 200 times faster than the manual labeling. And also, we have accumulated about 125 million label data set for the ADAS and ADS application. Currently, we would like to record multi-sensor data set for the autonomous driving, and that including the LiDAR, 7-channel camera, and also 2-channel 77 gigahertz millimeter waves radar signal, as well as the GNSS GPS sensor. And we would like to label all the data and then try to announce a Taiwan self-driving data set like the KITTI dataset format. And the next is the data augmentation. We call the easy augment that is embedded in the easy label. In the easy augment, that can generate the augmented data based on the computer vision method, including the Gaussian noise, motion blur, random crop, and different fisheye deformation. With the augmented data, you can increase the object detection model accuracy about 10% MAP. The next one is the easy model, which is a 2D and 3D CNN model pruning tool with user-defined quality as well as the pruning ratio. As you can see that you can reduce a lot of model complexity and model size at the cost of some accuracy degradation. And also easy hybrid model, which is a tool to develop the hybrid fixed point layer by layer big width CNN model. And it can achieve about 91% model reduction and the 76% bandwidth reduction under the example MobileNet SSD with the same quality. The last one is easy quant, which is a bit accurate layer by layer model quantization and the retraining tool. With the easy quant, you can develop the fixed point AI model with less than 1% MAP drop as compared to the floating point model. And the next one is the model porting on the AI SoC. So the model developed by our tool chain can be realized in commercialized AI chip. In addition, we also developed a hybrid fixed point CNN DLA to realize the model developed by our easy hybrid model tool. So our DLA can achieve 2.5 TOPS under 8-bit 550 megahertz, as well as the 20 TOPS under binary mode at 550 megahertz under TSMC 28 nanometers CMOS. From the energy efficiency, it can achieve 4 TOPS per watt in 8-bit mode, as well as 32 TOPS per watt in binary mode. All I want to do is that we can integrate the easy model, easy quant, and also easy hybrid model together to reduce the model complexity and power consumption. So with the example of VGG16 SSD model, we can achieve over 120 times model reduction, as well as 70 times power consumption reduction. Now, I will talk about the key components in our proposed AI decompression toolchain. The first one is fast data annotation. About the data labeling, we propose an easy label that supports the fast data labeling as well as the automatic data labeling. And the easy label can support the bounding box labeling, behavior labeling, and also the pixel labeling used in segmentation application. And it also can do the data measurement as well as the data analysis. Until now, we have over 660 registered users on Easy Label, and with about 87% users are not from our university. So here shows an example of our Easy Label auto labeling function. As you can see that the video that's automated label by our Easy Label tool. And as you can see that the quality of the label is good. And here shows the data set we had labeled before. It is over 125 million label data set for the ADAS and self-driving application. And the object categories are shown here, including the vehicle, pedestrian, cyclists, motorcycle riders, and also the landmarks and traffic signs in Europe and Taiwan, and also some obstacles in Taiwan, road construction, and traffic light, as well as some dangerous behaviors about the driving. Also, we have IVS Lab open data announced in the GitHub here. And this open data, we have about 96,000 frames of data set. And the data set include the different environment in city, highway, university, and country, and also different weather condition, clear, rainy, and foggy days, and also different lighting condition. And the object here including different kind of vehicles, humans, pedestrian, and also the scooter riders and the cyclist. With this data set, we have hosted 3 international object detection competition. The first is associated with MMSB 2019 pair competition, and we have 92 teams registered in this competition. And also, we host the ICME 2020 Grand Challenge pair competition, and we have more, about 133 registration in the second year. And also the third year, we host the ICMR 2021 Grand Challenge pair competition, and we have over 300 registration in the third year. Next, I will move on to the model design for Edge AI. So I would like to share some experience about the model design for Edge AI. The first is to simplify AI model with heuristic ways. And the second is to share base network for multiple task model we call MTSAM. The third one is use the model pruning through systematic approach that called the Easy Model tool. And also the model quantization through systematic approach using the Easy Quant. And the final one is the hybrid fixed point CNN model design used in our Easy Hybrid model. The first is to simplify AI model with heuristic ways. That's the example that we reduce the complexity by using the CSV net that is proposed by the YOLO V14 on the multi-head SSD. Here he shows that the CSV net architecture, you can divide the half the channels up in the convolution, and with half the channel go through the nonlinear operation, and the other half just bypass and then concatenate it together to go to the next layer. With this simple idea, you can diversify the features of the networks that have better accuracy in the model training, as well as you can reduce the complexity. So here shows the experimental result. And if you just use the multi-head SSD we propose, you can achieve about 49% accuracy. And the total MAC is about 3.3 giga per frame. And here's the number of parameters and his speed on the DDA to perform. If you add the CSV net together with the multi-head SSD under the same resolution, you can see that the MAP is increased to 78.72%. And also the total MAC complexity is reduced from 3.3 to 2.1 giga per frame. As well, the number of parameters has been reduced to 2.78 million. Of course, the speed is increased. The second one I would like to share is the base network for multitask model. Here, MTSN is a multitask model that we proposed. That means it is the multitask semantic attention networks for object detection and segmentation. Here shows the architecture. Here is the shared backbone, and then we have a segmentation subnet as well as the detection subnet. And we add a semantic attention module between the object segmentation and object detection. And we like to use the segmentation result to strengthen the detection feature map to increase the object detection accuracy. Because we think that the pixel classification, the accuracy is higher than the object detection in bounding box. So we just propose this kind of idea. And here shows the semantic attention module. And here shows some simulation result. And this is the input image. This is the segmentation prediction result. And this is the prediction without the semantic attention module. And this is the prediction with the semantic attention module. As you can see that for the small object here, with the semantic attention module, the model can detect some of the small objects shown here and also here. And here shows an example that we apply the MTSN model on the application of ADAS, including the LDWS and FCWS. And in this model, it can do the object detection as well as it can segment the landmarks as well as the main lane and the adjacent lanes as well. So with this information, you can do the lane departure warning and as well as the full collision warning system. Next, I will talk about the model pruning through the systematic approach that we used in our Easy Model tool, which is the automatic model pruning and retraining tool. In the model pruning, we adopt the structured and unstructured model pruning technology and try to remove the redundant operation in the CNN models. After that, we can do the model retraining to retain the model accuracy. Here shows the example that we apply the easy model pruning on the YOLO V4 model, and with different model pruning percentage from 10% to 90%. As you can see here, with the different pruning ratio, the prune model will have different model accuracy and also different complexity and model size as well as the performance. So we use the index called pruning score that is defined as the number of flops percentage reduction times the number of parameter percentage reduction and divided by the MAP drop. So the prune score is as high as possible. As you can see here, for the pruning ratio of 50% to 90%, the pruning score is over 300. As compared to the tiny YOLO V4 that's proposed by the YOLO V4 author, and a very compact tiny version, its pruning score is about 298. So that means that the prune model based on the ratio between the 50% to 90%, all the model pruning has a better pruning accuracy compared to the tiny YOLO V4. Here shows the result of YOLO V3 pruned by our easy model that is applied to the roadside unit application. So the application field dataset like roadside unit, it only has 6 class objects to be detected. So with the easy model, you can see that until the model pruning ratio to 70% and the model accuracy is still the same as the floating point one. For the real application, there is this much more redundant data operation in the CNN model that you can prune use the automatic method. And here shows the demonstration video of the YOLO V3. The upper one is the original model. The bottom one is the 70% pruning ratio YOLO V3 detection. As you can see here, the MAP of the pruned version is higher than the original one. And also, the speed is about 80% faster than the original one. And the subjective result shown here, you can see that the accuracy is still the same. There's no quality degradation in the prune model. And here shows an example of the model pruning on YOLO V4 that the prune ratio is 90%, and it is for the FCWS application. So the dataset will be only a 3 class, and that including the BDD 100K dataset, COCO dataset, as well as some company dataset. As you can see that the model complexity is as low as 0.89 gigaflop per frame, and the model parameter is 2.75 million, and the accuracy is 37%. After the model pruning, I would like to talk about EasyQuant, which is a fixed-point model quantization analysis and retraining tool. The EasyQuant can support the uniform dynamic fixed-point quantization, and as well as the multi-scale dynamic fixed-point quantization. And it is an automatic quantization tool, and it supports the layer-by-layer model development. And it can also be integrated with the Easy model. Why quantization is important? Here shows the impact of the post-training quantization. That means the direct quantization. And the right-hand side is a 14-point model, which we use the 70% from YOLO-v4. And compared to the 8-bit fixed-point model, you can see that the detection accuracy of the fixed-point model is a little bit worse than the floating-point model. I think that is caused by the quantization error. Here shows the experimental result that the multi-scale quantization versus uniform quantization under the mode of direct quantization. And the data set we use here is the MS COCO. As you can see that a different kind of model performance, including the YOLO-v4, YOLO-v3, and the YOLO-v3 Tiny. And using the uniform quantization, there's a lot of MMP degradation after quantized. And with the multi-scale quantization, which is a non-uniform quantization, you can have good correlation result compared to the uniform quantization. And here shows the comparison of the multi-scale quantization versus uniform quantization in the fine-tune mode. That means to do the quantization aware training. And here shows the YOLO-v3 and YOLO-v4 result. As you can see that if you use the multi-scale quantization and with the quantization aware training, the accuracy drop will be reduced within 1% compared to the floating point one, and which is better than the EasyQuant based on the uniform quantization, and also much better than the PyTorch quantization aware training. In terms of YOLO-v4, with the multi-scale quantization, it can have almost the same quality compared to the floating point version, and which is higher than the EasyQuant with uniform quantization, and much higher than the PyTorch quantization aware training method. And here shows the subjective result. Here shows the hybrid fixed-point CNN model development. And we developed a tool called Easy Hybrid Model for this model development. The motivation that we would like to develop this kind of model is that we found there's no need to have the same bit width in different layers of CNN model. For example, for the base feature extraction layer, you need 8-bit. But for the later layers, you just only need 4-bit, 2 bits, or even binary to do the classification of the features. So we take an example of the mobile net SSD, and here shows that the upper left one is the floating-point model, and then we try to develop a model based on the floating-point one to be the floating-point layers plus the binary layers, and then we quantize the floating-point layers into the 8-bit layers, and we retrain this model. So the result shows that if we have 25 layers of 8-bit layers and 12 layers of binary, we can have the same quality compared to the floating point one. And we also get the 91% model size reduction and as high as 76% memory bandwidth reduction. In order to support the hybrid fixed-point CNN model, we need to have accelerators dedicated for this purpose, because there's no existing AI accelerators that can realize the hybrid fixed-point CNN model. And our accelerators with the features of to support the 1, 2, 4, 8-bit waves activation based on the layer-by-layer option. And it can influence the AI model in bit accurate mode, which is trained by our EasyQuant and Easy Hybrid model. And the clock rate is as high as 500 megahertz, and the power consumption is 575 milliwatt. And the energy efficiency can achieve 4 TOPS per watt under 8-bit mode and 32 TOPS per watt under the binary mode. All the information is simulated at the TSMC 28nm CMOS technology. And here shows the performance evaluation on the proposed hybrid fixed-point CNN isolators. And as you can see that compared to the existing state-of-the-art design, and we can know that in the peak performance, 8-bit and binary, and also in the peak energy efficiency, 8-bit and binary, and also in the inference energy efficiency under the VGG16 model in both 8-bit and binary mode. And the proposed hybrid fixed-point CN isolator performance is good as compared to the existing state-of-the-art design. Next, I will talk about the EasyAIT, which means the Easy AI tool chain. The EasyAIT, it is combined with the Easy Label, which is automatic labeling tool with the Easy Augment option. And you can do the model training and pruning with the Easy Model and do the quantization training with the Easy Quant. After that, we also have an Easy Converter to do the model conversion from PyTorch model to Onyx model or to .NET model. And from Onyx, you can further translate the model to Caffe, TensorFlow, TensorFlow Lite, and also you can realize the model in different AI platform. And there's a GUI interface about the EasyAIT. All the users need to do is try to upload the video or images, and then try to select the open data set you would like to use together, and also try to select a different kind of augmentation option. And also you can select the model type and the model pruning percentage, as well as which kind of the model big width you would like to model to be. And then just click start. And the EasyAI tool chain can help you to generate the AI model automatically. Next, I will talk about the ADAS and AD applications that we apply our developed embedded AI technology. Here, the application include the ADAS application, the roadside unit application, also the autonomous driving application. The first is a multifunction ADAS. We realize on the our collaboration company Quanta Computer Qbox. So here you can see that we integrate 5 to 6 AI model together that can support FCWS, LDWS, blind spot detection, and BASIS warning system, as well as the DMS system. And the second one is the object behavior prediction. Here, we use an example of predicting the rear vehicle overtaking in the next 3 seconds. We combine the 3D convolution as well as the 2D convolution together and to predict the detected object's behavior if it will be overtake your car in the next 3 seconds. Based on the same architecture, we can apply it on the front camera, which can detect multiple object behaviors. And the behavior shown here, including the pedestrian crossing, vehicle cut-in, and also the vehicle emergency braking. As you can see that the same model can support the different behaviors with the high accuracy, over 94%. And here shows a 5G camera radar fused roadside unit for real-time traffic alert. And in this technology, we use the camera and the radar early fusion technology to do the object detection and tracking. And the proposed algorithm is realized in the embedded AI platform called NVIDIA Jetson Xavier. And here is our roadside unit box. And we install this roadside unit box in the roadside position. And the detected result will be shown in real time on the global map. And all the users can have the traffic information based on the 5G connected networks to realize the environmental traffics. And that could ensure the safety of the ADAS and the autonomous driving system. And here shows the experimental results of the proposed camera radar early fusion technology. As you can see that here we use the scale YOLO V4 P5 as the model, and we compare the result of using the RGB camera signal to the version that use both the RGB camera as well as the radar intensity together. And you can see that here with the radar information together, and the precision is 4.9% higher, and also the record is 3.6% higher, and the total MAP is 4.0% higher. So this shows that with the camera radar early fusion, we can increase the object detection and tracking accuracy in both the precision and recall. Here shows a distributed vector map-free autonomous driving system, which is based on the AutoWare and ROS operation system. As you can see that we use one industrial grade PC and three embedded AI platform Xavier together to realize the entire autonomous driving system. And here shows the features of this system is that it is vector map free. The vector map free means that for this autonomous driving system, there's no need to have the high definition vector map for the localization. So here we use the idea of a local sensing based on our proposed embedded AI technology to do the object detection, the landmark segmentation, and also the traffic sign, road sign recognition. With the local generated traffic information, that is helpful for us to know where the autonomous driving vehicle is, and it is helpful for us to do the path planning as well as to increase the accuracy of the SLAM. And as you can see, with the distributed system, the power consumption is about half of the centralized system, and its performance is roughly the same. So with this kind of vector map free autonomous driving system, you can reduce the total cost as well as there's no barrier for you to promote the autonomous driving vehicle to any place you want. Next, I will give a simple conclusion. Here, I would like to use the report from SRC to conclude this talk. As you can see that here is the evolution of the newer generation of AI hardware and algorithm. And the goal is to enable the co-design opportunity. And as you can see that the AI model becomes much more and more complex. And also the evolution of the AI hardware according to the technology evolution is also ongoing, but there is a lot of functional gap here. And also this gap can be considered as the toolchain gap we discussed today. So in the future, it is necessary to bridge the toolchain gap, and so that we can develop an AI model that can be realized in the embedded computing platform in real time. That's all my presentation. Thank you very much for your attention. Any question?